In this segment, we're going to review briefly a concept from algebra about composition of functions. If we have a function h of x equal to f of g of x, it would be a complicated function because there are actually more things involved than just, say, a linear function. What we can do is write this using the composition notation as f circle g of x. Now, this does not mean that x is multiplied by f times g. This is function notation, just like g of x is function notation. But these two mean the same thing. The function g is the function inside f, so that g of x is the inside function, and then f of x, or f of whatever, is the outside function. So let's look at an example. Where we have a function f of c equal to the natural log of c squared. It looks like one natural log function, except notice that inside the natural log function is c squared. C squared is inside. And that means the natural log part is outside. So I can think about that as two separate functions. If I wanted to find a value for the function, say f of c, instead of c, I'll put 3. That means I substitute 3 in place of c. I would have to square the 3 first and then take the natural log of it. So that would equal natural log of 9. Let's look at a similar but very different function. Suppose g of c is equal to ln squared of c. Now this says that the natural log part is squared, not that c is squared. So this really means take the natural log of c first and then square it. This is common notation that you will see a lot of. So if I wanted to find g of 3, that would be the natural log of 3 first and then squared. And if you check these numbers out on a calculator, the natural log of 9 is not at all the natural log of 3 and then square that number. Now, I didn't write an outside function and an inside function. I did not write them separately, but we can using what's called an intermediate variable. So let's look at an intermediate variable when we're working with composition. Suppose our function is p of q equal to 5 raised to the cube root of q. It's a little more complicated than ln of c squared. I have 5 raised to a power, so that part is an exponential function. So I can write this function as this part is the outside, and this part is the inside, where I have the 5 and then raised to a power. Let's say the inside always starts where the variable is. So wherever your input variable is, that indicates that's where you're looking at what's inside of your function. Let's call that u. Let's use the intermediate variable u to represent our inside function. U is the cube root of q. So my outside function p now is going to be 5 raised to the u power. Now note I didn't put p of anything. I sort of left the of part blank here, because in this case p is a function of u, and then u is a function of q. So I combine these as my function p of u, and u I could write as f of q. So this is 5 raised to the f of q power, and that gets us from p through the intermediate variable u down to q, just using u as the input, or down here I can write it with f of q as the input. So we can really see that we do go all the way to q. We'll see a lot more with intermediate variables in a little bit. Now we're going to look at complicated functions. You have the rules for derivatives for elementary functions. Now we get into the complicated functions rule, which is called the chain rule. But the chain rule is just a more complicated form of your elementary rules for derivatives. So let's first look at the chain rule when there is an intermediate variable. With an intermediate variable, we call this, if we have y as a function of u and u as a function, let's say g of x, then the chain rule using the intermediate variable u, where y goes to u and then u goes to x, we can write the derivative of y with respect to x as the derivative of y with respect to u times the derivative of u with respect to x. So we actually have two derivatives that multiply together to give us one derivative. Easiest way to look at it is through an example. If r is equal to q to the third power and q is equal to 3 to the n power, find the derivative of r with respect to n when n is equal to 2. We have to form a chain. We have the place where we start and the place where we end, and we have to relate the two in the middle. If you think about these as actually being fractions, what happens if you could, say, cancel du? You would have dy dx. So that's a way to keep in mind the way your chain is set up when you have different letters. So for the chain for this particular problem, we'll start off with the derivative of r with respect to n. And then we go from r to q. So we have the derivative of r with respect to q. And then from q, we go to n. So I'll multiply by the derivative of q with respect to n. So that according to what you used to learn from fractions, if you could cancel the dq's, you would have dr dn, and that's what we want. So let's get particular with these two functions. I'm looking for the derivative of r with respect to n. I want the derivative of r with respect to q. That means take the derivative of q to the third power. Power rule. Power rule for derivatives says the exponent comes around front times q to the second power. That's the derivative of r with respect to q. I multiply by, and I want the derivative of q with respect to n, so I come over here and I go, okay, 3 to the n, that's exponential. It's base 3, so it's the a to the u rule that says natural log of the base multiplied by the original function 3 to the n. So this is our derivative. Well, there is a little bit of a problem in that we have a q here and an n here, but we want the derivative with respect to n. What I have to do now is replace this q inside there with what q is actually equal to. However, I want this, which I erased, when n is equal to 2. I don't actually have to put in my function for q. I can just do my numbers. If I have dr dn evaluated when n is 2, let's go over to where we know n. I'm going to leave this part, put my ln of 3, and I have 3 squared because n is 2. But here I have 3 times whatever q is squared. So how do I find q? We go back up to q. Here's q. Q is equal to 3 to the n. So q is equal to 3 squared, which is 9. So when I have my q here, I come back and I make that 9. So I'm trying to find out what 3 times 9 squared, which is 81, is, times ln of 3 times 3 squared, which is 9. And work all that out, and it's supposed to come out to be something that is about 2,403. Now, the r's and the q's and the n's, you'll find out that this actually is a very basic type of way to talk about revenue. Revenue in terms of the quantity produced. Quantity is in terms of n being the number of employees. And so if we want the rate of change with respect to the number of employees, that can give us the way revenue changes depending on if you add an additional employee. So there are lots of different things that actually work with derivatives that is the reason we have complicated functions. The first part of the chain rule that we looked at used an intermediate variable, u. Y is a function of u, but u is a function g of x. So to get the derivative of y in terms of x, we have to go through the variable u. Now, if you look at the way this is set up, when we use no intermediate variable, it should resemble the result. If there's no intermediate variable, we write if y, let me call that a different letter, h, of x is equal to f of g of x. Then h prime of x is equal to f prime of g of x times g prime of x. So that I take the derivative of my outside function. F and h are the same. It's outside. I take the derivative of the outside part, but the inside does not change. And then I multiply by the derivative of the inside. So let's look at those outs and ins. X is the inside. So here I have my inside x. Here is my inside x. Here is my inside x. The x pairs with my g function. G of x is the inside function. G of x is the inside function. when I take the derivative of the outside, the inside doesn't change. I multiply times the derivative of the inside. Let's go back up to the one with an intermediate variable. Y is the outermost function. The u, which is the g, is on the inside. So again, my g is on the inside. The derivative of y with respect to x is the derivative of y, which is the outside. Like f is the outside. And then the derivative of u with respect to x, u is the inside function, just like g is the inside function. So basically, whichever rule you choose to use with the chain rule, you multiply the derivative of the outside function, where the inside is not changed, times the derivative of the inside function. So let's look at an example in the hopes that that makes a little more sense. Our function f of x equal to e raised to the power 1 over x squared. Now, to find out what is the inside function, start with a variable. Wherever the variable is, and here's x, that piece is the inside. So it looks like 1 over x squared is the inside function. And then what's left is e. So the e to the power is the outside function. So we have to think back about the rules for derivatives. 1 over x squared is the inside function. E to a power is the outside function. I have an exponential function, and I need that rule for derivatives, base e. I have 1 over x squared. That's going to be a power function. Now, the rule for derivatives for a power function doesn't have a fraction in it. So what I'll have to do first, sort of my scratch work, before I can get to actually the other derivatives, is to rewrite 1 over x squared as a function that I can take the derivative of using the power rule. Let's move some of this. 1 over x squared is the same as x to the negative 2. Now I can take the derivative of it. The derivative of x to the negative 2 is negative 2 times the x, and when you subtract 1, you get negative 3. Remember, you have to have all those basic rules memorized. We just keep moving forward using the same basic rules. My exponential function e to a power. If I'm looking for e to some power, we'll call it u. This is where we kind of get the two intermediate and non-intermediate rules combined. The derivative of e to the u is e to the u, or the derivative of e to the x is e to the x, just the basic part. When u is a big complicated thing like I have here, when I go to find my derivative, outside derivative times inside derivative. So to get f prime of x, I'll take the outside derivative. Derivative of e to a power is e to a power. That's the outside derivative, the derivative of the e part. The inside derivative is negative 2x to the negative 3. But it started off with the x in the bottom, so let's put the x part back in the bottom. And the inside part is negative 2 over x to the 3rd. So I've done the outside derivative multiplied by the inside derivative. And the inside part here, when I took the outer derivative, did not change. You don't usually see them left in this form. Probably you'd have the negative 2 on top of a fraction with the e, with the x to the 3rd in the bottom. So that's likely the way f prime of x would be written. Let's look at some more examples of the chain rule. That's the rule we use with our complicated functions. Suppose we have f of x equal to the natural log of x to the third power. And we want to find f prime of x. Now, when we're looking at a function that's not one of the basic derivative rules, which in this case would just be ln of x, that's a basic rule. Since it's an x cubed, we're no longer in the elementary function rules. We have to go to the chain rules. So we need an inside function and an outside function. Here's the x, so this piece is our inside function. So the inside function is x cubed. We use the power rule. The outside function then would be the natural log. So we take the derivative by taking the outside derivative times the inside derivative. So outside derivative means we have to think about the derivative of the natural log function. Natural log function, its derivative is 1 over x. But I don't have x on the inside. And when you do the chain rule, the inside x cubed doesn't change when it's just inside the natural log function. So my 1 over x would really be 1 over x cubed. Multiplied times, that's the outside derivative, the inside derivative. Well, the derivative of x cubed uses the power rule, so 3 comes around times x squared. So I have outside derivative, derivative of natural log, inside derivative, derivative of x cubed, and I can combine them. Now, if you just multiply, think of that over 1, you've got 3x squared over x cubed, but really, x squared over x cubed can be simplified, and you have 3 over x. Now, it is possible that you don't need to do a lot of simplifying, because sometimes what happens is, if you're doing a multiple choice question, the point of the question is not to see how much algebra you can do, but just to see can you take the derivatives. So we'll look at some like that also. Outside derivative times inside derivative. F of x equal to 3 raised to the power cube root of x. And be very careful when you read problems, because the exponents sometimes are small, and you want to be very careful that you know it's an exponent and not just 3 times the cube root of x. So I have inside function and outside function if I'm going to use the chain rule. This piece is the inside because it's where the variable is. And we have a rule called a to the x. For the chain rule, we could call that a to the u, where u is the inside function. And if I take my derivative, f prime of x, I need the outside derivative times the inside. And the inside derivative is going to require a little work because it's a cube root of x. The outside derivative is 3 to a power, so I have to remember the rule for the derivative of a to the x, or a to the u. There are 2 sets of derivative rules. One of them is written in terms of x. Those are usually the ones you use for the most inside derivative. And another set in terms of u. So I would have a rule for 3 to the u as well as a rule for 3 to the x. As you do the problems, you need to keep your little rules all beside you so you can check them constantly so that you'll have them memorized, because you do have to have all the derivative rules memorized. The outside derivative for 3 to a power is basically 3 to a power, but because it's not e, it's ln of 3 and then 3 to the power. The power here does not change. Whatever power you start with is when you end with, because this is the exponential rule. Then I multiply by the inside derivative. Well, the inside part here is the cube root of x. Cube root of x is x to the 1/3 power. So for the 1/3 power, I use the power rule the same way. 1/3 comes around front, times x, and you subtract 1, which gives you negative 2/3. Outside derivative, inside derivative. So we need to see if we can't simplify this a little bit. Since I started off with a radical, I might want to put it back as a radical, but I definitely don't want to keep a negative exponent. Let's see, ln of 3 to the cube root of x times 1/3 times 1 over x to the 2/3. The x is the only thing through the power, so it goes in the bottom. The 1/3 is already in the bottom. So I do have both of these terms in the denominator. So I think I'll just leave it like that instead of going to radical form. Once you get to about this point, if you're doing a multiple choice question, look at the answers, because sometimes you have to try to compare what all do I have in here. And something that will happen commonly has to do with this number that is 3 to the first power and this number that is 3 to the cube root of x power. You can actually combine these two because they are both base 3. So I can write my derivative as ln of 3 times 3 to the cube root of x minus 1, because the 3 that's in the denominator comes up to the negative 1 power. And then that x to the 2/3 is under everything. There are a variety of ways that algebra can be done to simplify problems or to make them look probably even more complicated. So once you take a derivative, before you start trying to do some algebra to change things, kind of check and see what the answer looks like, because that's the possible things you have to choose from. Now keep in mind, we are doing problems using the chain rule. This function, w of x, could be simplified. The square root of x to the 4th would be x squared, but then we wouldn't use the chain rule to get the derivative. So we want to use the chain rule, so we're not going to simplify this. To take a derivative, though, we can't have a radical, so we are going to have to rewrite this square root as a 1/2 power. And again, don't simplify. You could make the 4 times 1/2 because that is a power rule for exponents, but we're not going to do that. We're going to leave it like this and take the derivative. So when we take the derivative, I have part that's inside, so I use the power rule on that. And the outside is a 1/2 power, so I'll use the power rule on that also. Remember to take the derivative. We have w prime of x, and we need the outside derivative multiplied by the inside derivative. Okay? My outside derivative is a power, 1/2 times whatever is inside, and I subtract 1 from the exponent, gives me negative 1/2. That's the outside derivative. Now to do the inside derivative, I have x to the 4th, I take its derivative, and I get 4x cubed. So I have my outside derivative, my inside derivative, and that's what I have. Again, I end up with a negative exponent, so the piece that is attached to it, this x to the 4th, goes to the denominator. I have 1 over, the 2's on the bottom. This x to the 4th is now to the positive 1/2 times 4x cubed. And there are various ways to simplify. I'm going to basically leave it like it is, 4x cubed over 2, and I'm going to go back to my radical, square root of x to the 4th. Now, there's a lot that could be done here. I could cancel the 2 and the 4. I could do more simplifying, but I'm just going to leave it as I've done the chain rule and I'm through doing algebra. Let's look at a problem with a base that's not a number, an exponential function, f of x equal to e to the x cubed. So we're stepping up now, not just e to the x to the 3rd. We have a derivative rule for e to the x. we have a derivative rule for x to the third. So when you go to the variable here, this piece that includes the variable is what we have. We don't put the e to the x first and then put the power on that. The 3 is attached to the x, so that's how it's grouped together. The x and the 3 go together. So x cubed is the inside function. I could think of this as a function e to the u power. And if I want to find the derivative with respect to x, my derivative f prime of x will be the outer derivative, e to the u, multiplied by the inner derivative, which is the derivative of u with respect to x. So I have my outer derivative, that's my basic e to the x part, and the inner derivative, the derivative of that exponent. So you'll also see it written like this. The u that is the inside never changes. E to the x cubed, when I take the derivative, notice it's still e to the x cubed. And now I multiply by the derivative of u with respect to x, which would be the derivative of x cubed by the power rule, that's 3x squared. So this is my derivative. Suppose I want to find f prime of 0.98. I plug 0.98 in for x after I take the derivative. Anytime you're asked to find a derivative at a point, you have to kind of go in order, left to right. F, do the prime first. After you've got the prime, then you put the number in. So I have e to the 0.98 to the third power multiplied by 3 times 0.98 to the second power. Watch the order of operations when you're working this. Be sure that you plug things in, and you may want to write down intermediate numbers. Do 0.98 to the third, write it down. Then do e to that power, write it down. 0.98 squared multiplied by 3. You can probably get some of these pieces together depending on how you use your calculator. The answer here is supposed to turn out to be about 7.3846. So try it yourself to see if you can get those numbers when you're working on a basic scientific calculator. Now we're going to look at a function that looks worse than the other chain rule functions did, because this problem has more things inside. It has multiple compositions. The outside function is a 4. It's a power. So we have one outside function. But inside we have 5 raised to the ln x. So that's more inside. Usually we say to find the derivative of a complicated function, you take the derivative of the outside times derivative of the inside. Well, that's still what we're going to do. We just have to continue the chain a little bit longer. But let's start with the outside, which is 4 as a power. So I have f prime of x equals, power rule for 4 says 4, and you subtract 1 and you get 3, and the inside part stays the same, 5 to the ln x. So that is the derivative of the outside. Now we move to the inside, and the inside is 5 to the ln x. So I actually have more than one thing inside, but the x is here as the exponent, so it is the most inside of the inside, so we want the 5 to a power. So the derivative of 5 to a power, natural log of 5, times 5 to the same power, ln x. So that is what we could think of as our first inside function. That's the derivative of an inside, one of the insides. But we have our 5 to the ln x. So that is also inside of this part. So I multiply by the derivative of ln x, which is 1 over x. So I multiply outside derivative times inside derivative times the innermost derivative. and this would be what our derivative is equal to. Now, there are a lot of different pieces up here. Not sure that anything can be simplified. They can certainly be written in a different order because everything here is just multiplied together. So you take the derivative and then you just kind of try to match up your pieces when you check your answer when you do a problem. Let's look at another one that's messy. So we have e to the square root of the quantity 5x. Be careful with exponents because I have the square root of 5 times x, hopefully not the square root of 5 to the x power, but that could come up. So be very careful when you read a problem that you're reading the correct things on the inside. Now, this is e to a power. This x, where the variable goes, is inside, multiplied by 5, square root, and then the e. So the e would be the outside, and then we start working on what's inside. So to take our derivative, g prime of x, the outermost derivative is e to the u. The derivative of the e to the u is e to the u. So the inside part doesn't change. But now we have to multiply by the derivative of the inside. That's the derivative of the outsidemost part. When we started with the x, we said this piece is our inside. But that piece is a square root function. I can't even start taking the derivative of that until I rewrite the radical. So my square root becomes 5x to the 1/2 power. So I have a power inside here. So that's the next thing I have to take the derivative using the power rule. 1/2 comes around front times the inside stays. 1/2 minus 1 is negative 1/2. And I've taken the derivative of the inside, but there's still more inside because there's something inside that parenthesis. So now I take the derivative of 5x, which is 5. So I have an outside function, and then basically I have two inside functions, an inside and then another inside. So both of those have to have derivatives. We could rewrite this, especially because of the negative exponent. You probably won't see any answers that are just written in that form. So let's see what we can do with this. Took the outer derivative, my inside, my 1/2, multiplied by 1 over that whole 5x, which is now to the 1/2. Watch for parentheses. So let's see what I have here. E to the square root of 5x multiplied by 1/2 times 1 over that times 5. So I would say move the 5 in front, and I'll have 5e to the square root of 5x over 2 times the square root of 5x. And this condenses fairly nicely to give us an answer that may not be much simpler, but it really is smaller, maybe.